Okay, I wasn't really planning on doing a video on this originally, but this little mini fridge here is just so horrible. I had to kind of share my story and tell you kind of what happened with this thing. So my daughter got this thing for, I think it was Christmas this year. She plugged it in and she put some stuff in there. I think it was maybe an orange and some other nonsense, and started to smell something in her room. And turns out the thing was plugged in, but it wasn't cooling at all. I erroneously blamed my daughter, and I have to apologize for that. I thought she was using it improperly, but no, this thing was dead on arrival out of the box. Took it apart, found out that the power supply in the back, spin her around, the power supply that used to sit right down here, it's just a little open printed circuit board, was dead. There was no, I was getting 120 volts in, but I was getting 0 volts on the 12 volt side. So I ended up ordering a new 12 volt power supply off Amazon. This is by Meanwell, so this is a proper like UL listed component, high quality power supply. I'll leave a link in the description if anybody needs it. And thing cools perfectly now. So just real quick, I have 120 volts wired in here to line and neutral, and I have 12 volts DC out wired into this board right here. And this little board sends power to the fan, 12 volts, and power 12 volts to this thermoelectric cooler that uses the Peltier effect. This is pretty common on smaller fridges. No refrigeration or anything, or refrigerant in this fridge like there is in, like say your kitchen fridge. That said, I'm thinking about this thing, and it's still not a terribly good design. I should let there be light, right? And why is that though? Like, why is it a bad design? Because there's no temperature control. This thing's just going to run all the time, and when I stuck my fluke meter on there and measured the power, it was burning like, I want to say like maybe 30 or 40 watts of power non-stop 24/7. So I'm thinking to myself, that's pretty wasteful, right? I mean, this not a very big fridge, and it's just going to keep on cooling and cooling and cooling. So now I'm wondering, can we wire in a little thermostat and give ourselves some temperature control? So the way this bad boy works, and again, I have no idea if this is going to be good or bad, but we're going to try it. I believe the way these things work is they contain a tiny amount of some kind of refrigerant. It could be something that's more environmentally friendly than say R410A. Maybe it's just like butane, isobutane, propane. I don't really know what's in it, but there's some kind of refrigerant in there. And as the tip of this thermostat gets warmer, it closes the circuit and turns on the refrigeration component. So I'm thinking we take 120 volt power right here, send it to these two blade connectors, and this will break that circuit and just power down the whole thing once it gets cool enough. So it should be pretty easy for us to try that. So let's do it. So let's confirm some of my assumptions here. A little dish full of ice water. Let's grab our fluke meter and just confirm that this thermostat works the way I think it does, or that it works at all. So we got our fluke meter here. Boot it up. Hopefully you guys can see now. I'm just going to do a simple continuity test. So let's do over there. And it's not the meter I normally use, so I'm a little... Oh, wait, there we go. Let's try. So now it beeps when I touch these two probes, so that's what we're looking for. So let's open this bad boy up. I'm guessing that at room temperature we'll have continuity, so it should beep. And when we dip the tip in the ice water, I'm thinking it should open up. So let's stick our meter probes on here. One there. And one here. Kind of what I expected. Now let's dip this tube in here for a little bit and see if it stops. Wait for it. That's pretty annoying. Okay, so after quite a bit of waiting and actually dunking the entire probe in the ice water here, see our meter now says open circuit. So the probe did its job. Now let's pull it out and warm it up. We'll confirm that our meter starts screaming again. Might need to adjust this thing now. I don't want this, there we go. You heard it. Let's put it back in the ice water. And there it goes. Pretty cool how those things work, huh? Okay, so I'm just going to do a little test here. I have the thermostat probe thingy. I drilled a hole in the top of the cabinet right up about here. I drilled a hole in the back cover here. I'm going to temporarily screw it together and let it get really cold, and then check to see if the contacts are open or closed on the thermostat. If everything works out okay, then I'll make this situation more permanent and we'll wire it up. Okay, I got these two wires on either side of the thermostat. Just for testing purposes, you can see that the thermostat is now closed, 0.22 ohms. Let's turn this thing on to cold and walk away. Now you have to be careful with these thermoelectric coolers because you cannot run them unless they have a cooling supply to that heatsink. Otherwise they will burn out in pretty short order. So I'm going to walk away, let this cool for a while. All right, little update. I let this thing run for hours and hours and the thermostat never opened. So I ended up looking on this side of the thermostat, the side opposite of the electrical connectors, and there's a little Phillips head screw there. When I tightened that in a few turns, magically the thermostat opened. So you may have to adjust it from the factory. That's in addition to adjusting this knob right here. Turning it left makes it warmer. Turning it right makes it cooler. But yeah, this doesn't really seem to have any effect on whether or not the thermostat is open or closed. Try tightening in that screw on that side a couple of turns and see what happens. That might help. So right now, it's running nonstop. I don't have the thermostat hooked up electrically, but as you can see, it is open. Right now I'm doing a power draw test. So I want to run this for a couple hours and monitor the electricity usage with a kilowatt meter, which I have on the wall way back there. And so I'm essentially going to do a before and after energy consumption. So let it run for a couple hours like this, maybe. Let's see, what are we at now? Right about an hour and 15 minutes. And then once I have some run time on that, we'll take a reading and we'll install the thermostat electrically and we'll let it run, I guess probably for the equivalent amount of time and see how much energy it uses. Okay, so the little mini fridge here has been running for about 6.5 hours, as you can see here, and has burned about 0.28 kilowatt hours of energy. So I think I'm now going to cut power to it and make some of the modifications. And just to recap the modifications, I'm going to attach this thermostat to this back cover using these two screws. I'm going to replace the stock fan right here, which is kind of a low-end, not so nice fan. I think it might even be a sleeve-bearing fan, with this nice Noctua branded fan. They're used in computers all the time. That's what we're going for. I'll give you a link to that in the description too. And I don't have it right now, but it's on order. I'm going to get a limit switch and mount it to the heatsink. The reason I'm doing that is because these thermoelectric coolers, they work by transferring heat from one side of a plate to the other. So if this thing's constantly trying to dump heat onto this heatsink and this fan fails, you're going to melt down that cooler. I've seen that happen before on computer CPU coolers. So that limit switch is going to be mounted to the heatsink and actually open up the power circuit if this thing gets above a specified temperature. I used my thermal imaging camera and that thing seems to run at about, I don't know, like maybe, boy, I can't remember. I think it was about 90 degrees. We can actually check it right now, booting it up. Any day. This thing's a really cool tool, by the way. So much cool stuff you can discover in your house, all the gaps in your insulation and whatnot. So lots of fun. So let's remove the fan and just take a look at it, just real quick. So you can see The center of that heatsink right now is about 87.5 or so. Give it time, it'll get hotter though. So I ordered a kit of limit switches from Amazon, and we'll use those. We'll figure out which one makes the most sense, and we'll just wire that one into the power circuit. So let's get started. Oh, and I forgot to mention, I've had this cup of water sitting inside for all of those 6.5 hours. So this thing is now 42.1 degrees, about 42 degrees. Ambient in this garage is, I think, about 74, 75. See if I can warm this thing up a little bit. Sorry, you guys weren't seeing the fluke meter. So it's about 75 and change in the garage. And like I said, this water was 42.1. It's gone up a tiny bit. It's 43, 42.9. So yeah, you get the idea. This thing actually does a pretty good job at dropping the temperature down. All right, enough babbling, let's get started. Okay, first let's dismount our fan. We need a small Phillips head screwdriver. There's 2 screws, one at either end. Okay, off comes our fan. Take our new fan, mount it in exactly the same way. Well, that's not going to work. This fan's thicker than the old one. That's no good. Guess I'll have to revisit the whole fan thing another day. For now, this fan's going back on there. That's kind of unfortunate. Got my holes marked for the thermostat. Now it's time to drill. Okay, let's see if our screws fit through. If not, we'll just widen the hole a little bit. It's kind of what things are looking like here. Again, this is going to be the back of the fridge. You're never going to see any of this stuff. You can spend the time and make it look prettier if you want, though. Okay, now we need to run a wire from our power supply to our thermostat to open the 120 volt circuit in the event that it reaches temperature. Making some wires to go from the thermostat down to the power board. I thought I'd show you the process. That's kind of the finished product right there. I'll let there be light. So they're super easy to make with the right tools. So I'll show you how to make one. So you take your chunk of wire. Gonna cut off. This is number 14 wire. It's just what I had. It's not necessarily what you need. That's pretty much overkill for this. I'm redoing this connection because I found a split in the insulation right there. So you slip your wire terminal over the edge, like so. I'll give you links to these wire terminals and also these crimpers. These things are awesome. And they have like these color-coded jaws, and they also have different jaws for different types of wire. So you just put the connector in the crimper, squeeze the handle, and you're done. Now I'm going to move over here to the heat gun, and we'll shrink down this fitting. So just use the heat gun to shrink that up. It looks super nice. These wires are going to get hooked onto our thermostat up here, like so. There we go. They'll get routed down to our power board down there. And now comes the fun part. So we're going to take one of our wires, stick it under the screw on the power supply. Like so. Tighten that back down. We're going to take another one of our wires here, put that under the other screw. We're going to take our other wire from the thermostat and just connect these two like so. I'm just going to use a wire nut for that. Should do something like that. Like so. Trim off some of the excess. Then we'll screw our wire nut on. And that's pretty much it for wiring the thermostat. We will need to make some revisions when the limit switch arrives, but we'll cross that bridge when we come to it. For now, I'm just going to zip tie some of these wires and make them a little more secure. Something like that. That's about it. Now when our limit switch does arrive, all we need to do is undo this right here and just wire the limit switch in series with everything else, the thermostat, and then as long as something opens that circuit, that's what we care about. So that means that if the thermostat reaches temperature, or the limit switch detects a problem that is an overtemp condition, that'll shut it off too. We don't really care which one does it as long as both of those conditions are captured. In my opinion, that should be grounds for not allowing this product to be sold in this country by not having a limit switch, because you don't want this thing to catch on fire. And if that fan fails, you are at risk for that. So in my opinion, this thing is not even safe to use until you add a limit switch. But that's just my opinion. No one really cares what I think. Since we drilled a hole in the refrigerator compartment, I'm just going to take a dab of caulk and just kind of fill up that hole. Just do our best job to eliminate any air leakage. Because we're doing this for energy efficiency after all, right? Like, what's the point of this project if not for that? I'm going to do the same thing on the inside as well once we tape up that thermocouple. Just spread this goo around a little bit. Just a little bit of caulk, nothing fancy. Okay, let's put the cover back on. One of the downsides of this approach is that you're going to have to take more screws off when you want to take this thing apart, but I personally think that's a small price to pay. I don't care about that. Because you'll have to take the screws for the thermostat off as well as the perimeter screws. Again, to me, that's not a big deal. Be careful with the screws on, that's it. Not even one. That's it. And if you ever want to adjust the temperature, you just can turn this little knob right there. Nice and easy. Alright, so now let's get our screws on. I think I have one left in here. Down here. Just to hold it in place. And that power supply you guys saw, I just anchored that from the bottom. I'll show you the screws. Oh, sorry about that. So, little computer screw in the bottom. Looks pretty darn factory from the outside, don't you think? Pretty neat. Let's plug it in and see if it works. All right, here goes nothing. Oh, she's running. Pretty cool. So now, in theory, this thing should run for a while until it gets cool inside and then shut off. And then it'll sit there off until it gets warm again, then turn on, off and on, off and on, off and on. We'll be able to see that because this light should turn off because we're cutting power to our actual power supply. So that means this thing will be drawing 0 amps. Not even any parasitic loss through the power supply, which is pretty cool. And about half an hour later, our power light is off. You can make it go on by just turning the thermostat clockwise, and now it's magically on. Pretty cool, huh? So now I think it's time to do an energy measurement to see how much energy we're really saving here. I think I'm going to put a little cup of water in there and just make sure that our water temperature is about what it was before to make this a valid test. I think it was like in the low to mid 40s. So let me get a cup of water. I'll let it sit there for a couple hours. All right, I've had this mini fridge running for a while now. It's consumed 0.9 kilowatt hours in 28 hours and 37 minutes. So just over a day. So we'll go and we'll take a look and see what how that compares to without the thermostat. All right, I threw a quick spreadsheet together to just show where we're at with the energy consumption. As you can see, I got 2 columns here with no thermostat, with the thermostat, and the savings here. So per day, in terms of energy savings, that thermostat's saving you about 27% on your energy costs. Again, assuming temperature is held constant. That yields an annual savings of about $14. It's not a lot of money, but that if you keep this thing for 6 months, that pays for the part. The only part you need to achieve this savings is that thermostat. That thermostat's like $6 or $7 if memory serves. So you keep it for 6 or 7 months, this part pays for itself. So your son or daughter has one of these fridges, and they want to keep it for a couple of years, the savings adds up. It's a fun little project you can do with your kid too. So now that we've talked about all that, let's talk about making this thing safer. So let's install that that bimetal, oh man, what did I call it? One of these things. It's the thing that cuts the compressor off if, not the compressor, the thermoelectric cooler if the fan fails. So let's get this thing apart again. And again, we're kind of inconvenienced a little bit because to take it apart, we just don't have to take these 6 screws off the back. We have to take the thermostat screws off too. It's not the end of the world, but I mean, how often are you going to take this thing apart? This is very much a set it and forget it type of thing, right? And one thing we forgot to do before is they say that once you adjust that screw on the side of the thermostat, you have to put some glue. They call it glue. I'm just going to use some Loctite on the threads to prevent it from sorry guys, it's Friday afternoon. I can't talk anymore. What's holding us on here? Yeah, they don't want that adjusting screw backing out. So we'll take care of that while we got it open too. Gonna go ahead and blob some blue Loctite in there and probably make a mess in the process. It's a really tiny screw. I think that'll do it. Way more than we needed. Okay, so I bought a variety pack of these like thermistor things. Or not thermistor. What do I keep on calling these? These are those devices that open up when they get too hot, whatever you want to call those. So I found one that opens up at 45 degrees C, and it just so happens to fit pretty much perfectly inside the heatsink right here. I don't need to attach it. I mean, it's sturdy. So I think we'll just leave it like that. I mean, if this thing really gets hot, that should be just fine. Push it maybe a little farther. Perfect. So now you just have to use this to break the circuit. Let's confirm that actually makes a circuit first before we go into that. These should be normally closed, but let's confirm. Got our fluke meter here. Let's just hook up and see what the resistance is across these. These are good for, I think, 10 amps, if I recall. Works for me. 0.14 ohms. That should do just fine. So now we just have to wire this bad boy in the circuit for the 120 volt power supply. They are rated for 250 volts, if I recall. That says somewhere. This is all in, I think it's Chinese. I don't know. I'm not sure what language that is, but it says it on the Amazon listing. So now we'll undo this connection here. And we'll just wire this in series. Wrap this wire around this way, maybe. Probably should have given a little bit more thought into the routing of these wires, but it is what it is. I think I need to strip off a little bit more of these wires. There's not a whole lot of meat exposed. Easily done. So we'll shorten this wire here. Bring it to maybe about there. Okay, so we'll take another wire nut. We'll wire nut these bad boys together. Definitely did not have to use number 14 wire here, but what I had on hand, right? Use what you have. Now you might argue that's not making good thermal contact with the heatsink, and you might be right about that. But I would argue it's probably good enough. This thing's going to heat up. It's going to heat up enough where it's going to make a difference. Use a smaller wire nut there. Let's use a blue one. Those wires are smaller. Well, that should do it. Okay, there's our finished product. I got our cutoff switch right here. Got everything wire nutted in there. I think it's time to close it up, give it one final test, and call this project complete. That was kind of fun, right? Well, these fridges are really popular with the kids, so never want to say no to your kids, right? Dad, I want this, I want it, I need it. There you have it, folks. This thing's just about put back together. So we spent a very small amount of money on this thing. I think that bag of thermal cutoff switches was maybe, let's say maybe they're, oh boy, I don't remember. It wasn't expensive, maybe $7 or $8. So for $7 or $8, we made this thing about 27% more efficient. Was this 27? Yeah, 27.5% more efficient. Saving some money, and we made it safer. So in theory, if this fan ever were to fail, that heatsink would get hot, and that little thermal cutoff switch will open the compressor circuit. I keep on saying compressor. The thermoelectric cooler circuit, actually it's going to open this circuit, the 120 volts. It'll open that, so it'll shut the unit down if it ever gets too hot. So now we don't have to worry about this thing overheating, in theory, assuming that product works correctly. But anyway, I know these fridges are really popular. Hopefully this gives you some insight into how they work, some of their weak points, some of their strengths, the only one really being cost and size, and how you can improve upon the factory design and make it better. Again, I think I mentioned before, I read online that a lot of these things out from the factory are dead, like they just don't work, just like this one. And the culprit's really that power supply in the bottom that I replaced before I even started this video. I'll give you guys a link to that as well, because that thing works pretty well, and it's a high quality power supply from a reputable vendor. You don't have to worry about that one. Anyway, enough babbling. Hopefully you found this video helpful. If you did, please subscribe, stay safe, and thanks for watching, everybody. Take care.